Hello everyone. It is my pleasure to introduce all viewers to our paper on random forest based capacitance prediction in electrochemical double layer capacitors. The paper has been written by A. Guru, V. Rajeghatge, S. Krishna under the guidance of Dr. R. Mishra and Dr. T. Roy. All of the authors have contributed equally and the paper is a result of their hard work. As students of Birla Institute of Technology and Science, one of the most prestigious institutes in India, we are extremely glad to present our paper at the second International Conference on Energy and AI. Without further ado, I would like to discuss our research in detail. In our presentation, we will be covering an abstract of our research, introduction to EDLCs, feature selection, the model used, K-fold cross verification, results, and conclusion. Due to the ever-growing need for energy consumption, newer and newer technologies are needed for the storage and replenishment of power. In this paper, we have analyzed electrochemical double-layered capacitors, henceforth referred to as EDLCs, due to their high power density, rapid charge-discharge cycle, and long cyclability. The problem, however, is that the capacitance of an EDLC is hard to mathematically calculate due to the absence of an empirical relationship between capacitance and other physical attributes of the EDLC. In our study, we have tried to estimate the capacitance of EDLCs using a random forest algorithm alongside 10-fold cross-validation approach. We have used 194 datasets in total, consisting of data points collected from previous literature. The features or attributes of the EDLCs that have been considered are electrode specific surface area, electrode pore volume, electrode pore size, IDIG ratio, and potential window. I will be explaining this in detail in the following slides, but first, let me speak a bit about batteries and EDLCs. The swiftly increasing global energy consumption and the environmental impact of utilizing the traditional fossil energy sources pertain to tremendous increase in the research activities for clean and renewable energy sources. The rapidly growing demand for electricity adversely affected the environment as human civilization became dependent on carbon-based fuels. Electricity is a vital commodity for the world to function, and an optimal way to store and generate electricity has been a pressing concern. Lithium ion batteries are currently used, and they manage to boost storage and extraction of electricity from intermittent renewable sources like wind, tidal, and solar. Lithium ion batteries are one of the major power sources to electronic devices, smartphones, automobiles, and other parts of our lives. However, the life cycle analysis of lithium ion batteries show that they do cause a negative effect on the environment. The three main disadvantages of lithium ion batteries are their low to moderate power densities, short life cycle, and toxic electrolytes. This especially hampers their application in transport and industrial sectors. Electronic double-layered capacitors are a type of energy storage devices that are capable of integrating with lithium-ion batteries in hybrid energy storage systems. As a result of this, they are able to overcome the limitations of lithium-ion batteries. These EDLCs are specially designed capacitors with huge capacitance value and energy densities as compared to normal capacitors. They have several additional advantages like huge power density, long cycle lives, fast charging capabilities, and storage capacity roughly one-fourth energy by weight. Electronic double-layer capacitors mostly use liquid electrolyte, either aqueous or organic, and activated carbon as electrode material due to its large specific surface area. As voltage is applied across the cell, counter ions from electrolyte move towards the electrode and form a double layer at the electrode electrolyte interface. Formation of double layers along with an increase in surface area leads to higher capacitance, thereby higher energy densities of EDLCs. There are several factors which affect the performance of an EDLC, specifically their capacitance. These factors are specific surface area, electrode pore size, electrode pore volume, potential window of electrolyte, and the ratio of IDIG. SSA refers to the specific surface area of the carbon electrodes, and it is necessary to increase the SSA in order to enhance the capacitance. PS refers to the pore size of the electrode, which affects the accessibility of the electrolyte ions. PV refers to the pore volume, that is, the volume of the pores of the electrode. PW is the potential window, which is the voltage applied across the supercapacitor. ID by Ig ratio is the intensity ratio between the D and G bands of Raman spectroscopy, giving an insight to the crystalline properties of the carbon used. Traditional double layer theories are confined to mathematical derivations for flat electrodes. It is difficult to track the effect of pore network on the capacitance of EDLCs. Molecular studies are possible to analyze porous structure effects. However, the time scale and length scale for such simulations are far from reality. Also, experimental approach for fabricating electrodes with different dimensional aspects is time consuming and a costly affair. Therefore, there is need to predict the capacitance by considering the parameters of carbon-based electrodes as well as other parameters that can help in enhancing the capacitance. We have used random forest algorithm with standard scaling. The random forest is an ensemble approach that can also be thought of as a form of nearest neighbor predictor. The random forest starts with a standard machine learning technique called a decision tree, which, in ensemble terms, corresponds to our weak learner. Instead of relying on one decision tree, the random forest takes the prediction from each tree and based on the majority votes of predictions, it predicts the final output. The greater the number of trees in the forest leads to higher accuracy and prevents the problem of overfitting. Random forest is a joint prediction approach in the sense that it combines the results from each tree and averages their individual predictions, thereby reducing the risks of large errors in the model. The advantages of random forest are clear. It takes less training time as compared to other algorithms. It predicts output with high accuracy. Even for the large datasets, it runs efficiently. It can also maintain accuracy even when certain data points are missing. In our research, the prediction performance for random forest is measured based on two evaluation indices, namely the correlation coefficient R and root mean square error RMSE. The equations are shown in the figures. Additionally, a commonly used validation method called the k-fold cross-validation method has been used in this study. This is particularly useful while comparing various machine learning algorithms. In this approach, the dataset is divided into k subsets, wherein k-1 subsets are used for training and the rest for testing the model. This partitioning is random, and different iterations will consider different k-1 subsets every time as the training data and the remaining as testing dataset. For this study, k equal to 10 has been used. Thereby, it is called 10-fold cross-validation. The instances from 9 folds were used for training, while the remaining fold was used for testing. Based on the random forest algorithm, EDLC capacitance was predicted, and the figure shows the variation of the actual and the predicted values of capacitance. The evaluation indices R and RMSE are also indicated in the figure. The values of evaluation indices are very close to that obtained in previous literature while predicting EDLC capacitances using various machine learning algorithms such as regression tree, support vector regression, multilayer perception, and linear regression. This proves that the random forest algorithm predicts the EDLC capacitance with fairly good accuracy. A tenfold cross-validation has been used alongside RF in order to use it for future study for comparing with various machine learning algorithms. Once the capacitance prediction model was established using the random forest model framework, the individual feature contribution was also analyzed. This figure shows a pie chart featuring the individual features along with their contribution towards determining capacitance. It can clearly be seen that the specific surface area plays the most vital role in enhancing capacitance by around 37.26%. The second most important feature is the pore size. This indicates that to enhance the capacitance, reduced pore size is favorable, as this will lead to the formation of a thick double layer, therefore high capacitance, which in turn helps in increasing the specific surface area of the electrode, thereby also enhancing capacitance. Interestingly, the smallest contribution towards enhancing capacitance is the potential window of the electrolyte, only by about 10.21%. This indicates that irrespective of using ionic liquids or a high potential window electrolyte instead of conventional aqueous or organic electrolytes, its effect in enhancing capacitance will be much lower as compared to enhancing the specific surface area of electrodes in EDLC. I would like to conclude our presentation with summarizing all of the points that were discussed above. In the present study, capacitance prediction of EDLCs was carried out using random forest algorithm with a tenfold cross-validation approach. The developed model could predict the capacitance with reasonably good accuracy. Moreover, analysis of features identified in the study indicated that the specific surface area and pore size influenced the capacitance significantly by figures of 37.26 and 21.43% respectively. The study also highlights that reduction in pore size improves capacitance as it increases the specific surface area and helps in thick double layer formation. The lowest contribution in enhancing the capacitance was observed while varying the potential window of the electrolyte. The study provides a base for adopting an experimental approach to analyze the identified research gap. With this, we come to the end of the presentation. I would like to thank all viewers for listening and wish everyone a good day ahead.